Exercise 1811 is asking you, it gives you a whole bunch of different molecules, and it's asking you whether each of these molecules are aromatic, non-aromatic, or anti-aromatic. And we're going to follow that same process of reasoning that we've used in the last couple problems and that we developed in the video on the concept of aromaticity, anti-aromaticity, and non-aromaticity. The two notes, I guess, that you should make here are that first, if you have a positive charge, that is in an empty p orbital. And that should make sense because if you have a carbocation, the carbocation is trigonal planar, and so sp2 hybridized. Remember, the hybridization and the shape always go hand in hand, so anything that's trigonal planar will be sp2 hybridized. And so those carbocations are sp2 hybridized, which means that they still have one p orbital that's not mixing with the other orbitals. Now, if you have a positive charge, that p orbital is empty, but you still have it there, or at least as a possibility. And so you want to consider a positive charge as an empty p orbital. And second, if you have a lone pair, that lone pair in these examples will exist in a p orbital. So that also will count as a p orbital. So when you're assessing this first question, are there parallel p orbitals on every atom in a ring? Just keep in mind the positive charge is a p orbital and the lone pair can be a p orbital. Otherwise, we're just going to go through this process of reasoning for each of these molecules. So first, our first molecule A, are there parallel p orbitals on every atom in this ring? Well, we definitely have parallel p orbitals on the two carbons involved in the pi bond. It's those parallel p orbitals that create the pi bond. And then we just said that these lone pairs will exist in p orbitals. So that's parallel to the others. And so you have a p orbital. In this case, they're all vertical on every atom in the ring. And so you end up getting the answer yes to that. So we go on and ask the next question. The number of electrons in those p orbitals, is it 1 in that series of 4n plus 2, one of those Huckel's numbers? And here, we'll count them up. We have 2 electrons from the pi bond and 2 electrons from the lone pair. Those are all the electrons in those p orbitals. So 2 plus 2, we have 4 electrons in the p orbitals. Is that in this series? And it is not. If you plug in 0 for n, then you get 4 times 0 plus 2. The first number in that series is 2. If you plug 1 in for n, then you get 4 times 1 plus 2, that's 6. The next number in the series is 6. And so you skip over 4. Now remember, n does not mean any physical thing. It's summarizing an infinite pattern with an algebraic expression. It's not a physical thing. What is significant, physically significant, are the number of electrons in the molecular orbitals, and that's this final number that you get in these patterns. If you have one of those numbers of electrons in the p orbitals, then when you draw out the Frost circle and you see the molecular orbitals, all the electrons will pair up in stable orbitals. And if you don't have those numbers, then they're going to be unpaired in unstable orbitals. The molecule will be especially reactive. So here, because we don't have a Huckel's number, because that 4 is not in the series of 4n plus 2, this is not going to be stabilized. This is going to be especially unstable. It's going to be anti-aromatic. So let's use that same thought process in for this next molecule. Okay, this next molecule. First question, are there parallel p orbitals on every atom in the ring? And there are. There are parallel p orbitals in the pi bond. That's what's creating the pi bond. And then we said that positive charge is an empty p orbital. And so those electrons will be able to fly all the way around the ring. There are parallel p orbitals on every atom in a ring. So you'll get those molecular orbitals in a ring. So yes. Second question, are there 4n plus 2 pi electrons? Let's see. We have 2 electrons in the bond. We don't have any coming from the positive charge. So that's a total of 2 pi electrons, or 2 electrons in p orbitals. Two is a Huckel's number. If you plug 0 in for n, then you get the first number in the series, which is 2. So this is a Huckel's number. That means that if you were to think about the molecular waves that can wash over that ring and how electrons fit into those waves, because it's 2, all the electrons will be paired in stable orbitals. And so, because you do have a Huckel's number, the molecule is aromatic. It's especially stable. Okay, we're going to use that same process of reasoning on this next molecule. First question, are there parallel p orbitals on every atom in the ring? And there are. You have parallel p orbitals on each of the carbons in the double bond. That takes care of 4 of the 5 atoms in the ring. And remember, the positive charge is an empty p orbital. And so the charge in the electrons in those p orbitals are going to be able to flow around the entire ring in large molecular waves. So they'll form those special waves that will make the molecule either really stable, aromatic, or really unstable, anti-aromatic. And we can tell the difference between those two based on the number of electrons that are flying around. If we have 4n plus 2 electrons in the p orbitals, then it will be especially stable. And if we don't, then it'll be especially unstable. Well, here we have 2, 4 pi electrons. Notice there are no electrons in p orbitals from the positive charge. So we have 2 electrons in p orbitals. I'm sorry, we have 4 electrons in p orbitals, 2 from each of the pi bonds. So we have 4 electrons, and 4 is not a Huckel's number. Right, if you plug in 0 to this, you'll get 2. If you plug in 1, you'll get 6. Notice you skip over 4. So 4 is not a Huckel's number, and so the molecule is anti-aromatic. It's especially unstable. Okay, we'll apply that same process of reasoning to D. Excuse me. So here the first question is, are there parallel p orbitals on every atom in a ring? Every atom in the ring. Well, we definitely have them on all of the conjugated pi bonds. That takes care of most of these. And then you just have to worry about that lone pair. We said that lone pairs can exist in p orbitals. And they will exist in p orbitals if they create aromaticity that way. They'll fly around in whatever way gives them less energy. And so if they're fly around in a p orbital, that'll give them less energy because it'll potentially give them less energy because it would let them flow around the whole ring in the molecular orbitals. Okay, so we do have parallel p orbitals all the way around the ring. Second question, are there 4n plus 2 electrons in those p orbitals? Well, let's see. Let's count them up. We have 2, 4, 6, 8, and 10. Note that the lone pair is in a p orbital, so that counts. We have 10 electrons. And 10 is a Huckel's number. 10 is included in the pattern of 4n plus 2. If you plug in 2 to that equation, you get 4 times 2 plus 2. That's 8 plus 2, that's 10. So because this is one of the numbers in that pattern, when you draw out the molecular orbitals and you fill all the electrons in, you'll see that all the electrons will be in stable orbitals and they'll be paired up. So that this molecule, because you have those 4n plus 2 pi electrons in p orbitals, it's aromatic, it's especially stable. So you can see how you can use this process of thinking that we developed in the video on the concept of aromatic, non-aromatic, anti-aromatic. You can use that to figure out whether all these weird-looking molecules are especially stable or especially unstable, aromatic or anti-aromatic.